today we will be talking about the thing that I forgot to talk with you about the last time, which is Eulerian circuit, and then we will talk about the shortest path algorithms. That's I should have told about Eulerian circuit last time, but it didn't came to my mind, unfortunately. Okay, so what is Eulerian circuit? So you are given a graph, and Eulerian circuit is the path that visits each edge only once and finishes at the same node. There is always Eulerian path that should visit all their edges once and probably finish in some other vertex. But circuit finish in the same. So for example, this graph is like the graphs that has Eulerian circuit are named Eulerian graphs. And they have a special property. So we have undirected graph. Each degree of the vertex, degree, should be divisible by 2. Otherwise it is impossible to build a Eulerian circuit. Why so? You can think of, suppose we have a Eulerian circuit, then since it is a circuit, you come to each node and then you go away from this node. So if you consider one vertex, how the Eulerian circuit looks like. So it comes one way through the vertex V, then probably another way through vertex V, then probably another way, and etc. And you can see that their incoming edge always has outgoing edge, so that is why their degree should be even. Luckily, this problem is not in P hard. We already talked about Hamiltonian path, where we should have visited each vertex once. This is a little bit different. We should visit each edge once. So this problem appears also in bioalgorithms, where you want to restore the DNA. So you have reads like A, E, C, A, something. You have some reads of length K. And you want to have a DNA that has all these reads. So specifically for that, we built a de Bruijn graph. What it looks like. We just get the first k-1 symbols as the vertex. And so we have a vertex A, G, C, A, blah, 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 blah. And then the vertex starting from here. So it is G, C, A, blah, 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 blah. And it has an edge because outgoing edge. So after this, the next symbol will be this one. Like then CG, so it ends with C, and this one ends with CJ. So and then you just have to find the Eulerian path in this graph, and this will be your kind of DNA. So that is how the reconstruction, how briefly the reconstruction works. I think you will be explained it in more details on their bioinformatics algorithms. So, okay, we were talking about the Eulerian circuit. What is the condition for Eulerian path?
Well, a similar condition to the number of degrees.
Okay. And?
Well, I guess we could have one vertex, I think, or two vertices, which would not have a degree divisible by 2.
Yeah, exactly two vertices. The start of the path and the end of the path. Everything else should be divisible by 2. So yeah, of course, also it is clear that in directed graph, what the condition should be for each vertex.
The number of incoming edges should be equal to the number
of incoming should be equal to outgoing. So like their incoming degree is equal to their outgoing. So how do you think we can build Eulerian circuit? Like it's pretty simple. So I don't know how to save this graph. I think something like that should be, yeah. So suppose we know that the graph has Eulerian circuit, Eulerian path, so we know from which vertex to start. In the circuit, we can start from any vertex. In the Eulerian path, we can start from the vertex which is not divisible, which degree is not divisible by 1 or by 2. So how to start it? The simplest idea is just to follow like incoming and outgoing edges. You just go by some outgoing edge, then again by outgoing, then again, then again, then again, then again. Okay, so you find this cycle, but it is yet not Eulerian, because you kind of like if you took like this way by everything, you can visit not all the vertices, but still there like the graph still be Eulerian, because you will be left with again Eulerian circuit, because if you remove these edges, the graph still remains Eulerian, because the number of degree is still divisible by 2. So but it will be not connected already if you throw away this graph. So you have to know that kind of you have to merge these cycles together in order to get the whole cycle. So you would think that, okay, we go by one cycle, throw away, then take another cycle, throw away, and etc., and then merge it back together. So that would be the simplest idea that comes to mind, because you will always get to the cycle, because their outgoing degrees are divisible by 2. So for each incoming edge you have outgoing edge. The trick is that we can do it using the DFS. We can do the whole thing using DFS. And it appears to be pretty simple. So you'll learn. The B, add V just to restore. So we go for each edge, for each outgoing edge, and if their edge is not yet visited, we visit it and call recursively with u, and then add v to our Eulerian cycle. So how will it work here? So we will go recursively to this end, and then you go back, you add this edge to the answer, then you see that you go recursively to this cycle, then you go by that and finish here. Then you add this edge on the way back, this edge, and this edge. So kind of you already merged them together, these cycles. Then you go, when you return, you add this edge, and you get their continuous Eulerian circuit. What is wrong with this algorithm? Any ideas? I mean, why it is slow? So we want to work in the DFS time of m, where m is the number of edges. What do you think will be the complexity of this algorithm in the worst case? Oh yeah, so there is a mistake. I should add only once. I think. Yeah. So what is the complexity?
I guess maybe something like number of nodes multiplied by number of edges.
Yeah, kind of like that. Because the problem that each time we go over all the edges, and if we get to the vertex several times, we can unfortunately go over all their adjacency list while visiting each edge more than once. To solve this issue, we should use a special like d of v is the how many edges we already gone through v, how we already passed through. So then, while d of v less than deg v, then we say u equals edge from v d of u, and you make u plus plus dov plus plus Eulerian v and then ans dot add v dot Eulerian u. So right now we take the last edge which we already know that we have not visited. Yeah. So we take this edge and then we go, if this edge is not visited, then we say that it is visited and increment the number of the degree. Oh. No. Something is wrong here. I should do it here. So you get an edge, you increment the number of edges which we already passed for the vertex v, and then if this vertex is, if this edge is not visited, then we set it to visited and go recursively. There is one more complication to this algorithm, is that in directed case there is no problems with that, because you just go over, this will be over outgoing edges. But in the undirected case, you have edge kind of from u to v and from v to u, and you should pass this edge only once. So this vu dot visited is a little bit more complicated, because kind of you should visit vu and uv at the same time. So it is better to store it as edge class. So you have an edge. So you will have an edge class which has int uv, and then you say boolean visited, and then you like write the function to v return, oh sorry, w, let it be w, then u equals w, then return v, otherwise return u. And then when you create an adjacency list, you create like new edge of uv, and then you say eu dot add x and ev dot add x. So by that you kind of add the same class, the same object to e of u, or there to the edges of u and to the edges of v. And then when you set vu to visited, you will set as the correct edge and the backwards edge. So that's a little bit complication here. Luckily, this algorithm already works in linear time on the number of edges, because you visit each edge only once. Because you always increment this guy here, and you always gone through the vertex twice, particularly in one direction and in another direction in the worst case. So anyway, it will be the number of edges. So yeah, this algorithm is not so easy. So like the algorithm for the time n times m is easy. So you just go recursively and don't care about anything and just add the vertex v at the end. In the case when you want to have a normal complexity of the number of edges, you just have to insert the current non-visited edge for each vertex. Is it clear? Or are there?
Yes, I think.
Are there any questions? I think you will have to write the simple version. Like this one is already a little bit more complicated for you probably, because you have to know like these classes and etc. While I'm not sure that you're really familiar with programming. Of course you're familiar with programming, but I don't know whether it is easy for you to write that. Okay. That's about Eulerian circuit. And then finally we will come to the last topic of our course is shortest distances. We start with the simple problem. You are given a graph. Unweighted. Like there are no weights at all in this graph. It will be they will be added later, but right now we don't care about that. And you want take some edge, some HV, and calculate the distance from this vertex V to all other vertices, the shortest distance. How to calculate their distance? So in unweighted graph, each edge costs 1. In weighted graph, you will be given the weight for each edge separately. But we start with unweighted, so like each edge counts as 1, and then distance here is 0, distance to this node is 1 to this node, 1 this node, 2, and this node,
3.
Okay, great. So okay, we already did the algorithm in there that we're going to look like that. So the algorithm is breadth first search. So why it is different? Because in depth first search we always go like by each edge down. This algorithm is a little bit vice versa. We kind of take a vertex V and then take all outgoing edges of it, and then we store their vertices that are kind of on the first level. So you kind of vertex V here, and then you take all the neighbors. All of them will be on distance 1, of course. Then we take all the neighbors of these neighbors. Some of them can coincide, but we will talk about this later. Suppose we store vertex only once, so we don't have to worry about anything. So this will be the distance 2. Then if we take, again, the neighbors of this guy, and all of them, the neighbors of their second level, we have the 3, and so on. Of course, if, for example, it is possible that in this level, like the neighbor of this guy is some vertex from 1, so we don't count it twice. So each vertex appears only once and on the level that is the highest possible. So can you tell me, so we have this tree, creation tree using this BFS. Can you tell me, is it possible to have an edge between these two levels, 1 and 3? Is it possible that there is an edge between some vertex in 1 and some vertex in 3?
No, because we visited all the neighbors of 1 in the second level.
Yeah, exactly. Kinda, if it has an edge, then this guy should be on level 2. Okay, is it possible to have edges inside the level?
Yes, I think so.
Yeah, good. So now you approximately understand what's happening here. So how to write this algorithm? Like, writing the algorithm as it is a little bit complicated. It's like maintain the frontier of the vertices is a little bit more complicated. Then we create a queue and add their v and say dv equals to 0, while all the d's are currently -1s at the beginning. Then, while q not empty, we get u equals q dot poll. So we take the first guy in the queue and iterate over all its neighbors. For uw in E, then we say if d of w equals to -1, then say dw equals to du plus 1, and q dot add w. So on each iteration, we take some guy from the top of the queue, from the left of the queue. Then you iterate over all the neighbors, and if we yet not visited this vertex, so dw is equals to -1, so we don't know the distance yet, we set this distance to +1 and add this to the queue. Why it is working, you could have asked. The interesting part is that if you look over how the vertices, like suppose we do not throw away the vertices after we poll it, so we kind of have infinite queue that has like the start and their current head and the tail. Tail. The interesting part is that how this queue will look like. It will start with the v. Yes. Okay. Then you will start from all the vertices on the distance 1, because you add all the neighbors. You add all the neighbors that are in distance 1. Then it will be all the vertices on the distance 2, because each time you take a vertex from 1, you can only create vertices 2, like on the second level. Then 2, then 3, and etc. So they kind of this is the frontiers, but in a little bit more skewed way. Kind of you don't know exactly what the frontiers are, but you emulate the frontiers in some sense. So, and that is why in du you will have the distance from the vertex v. What is the time complexity of this algorithm?
Well, I think it should be also the number of edges.
Why? Why it is linear to the number of edges? Yeah, I mean that's correct. Like why?
Well, because once again we go through each edge once and add the vertex to the queue if it exists, and if not.
Yeah, I mean probably twice for each edge, because in both directions. You can visit one edge in both directions. Kind of, you can visit from u to w and from w to u, but you will never add this vertex the second time. Okay, so that's how to find their shortest distance in their graph. There is an interesting problem that is similar to BFS, is that suppose right now you will have weights on edges, but only zeros and ones. So for example, for this node it will be 0, for this node is also will be 0, because you can go by these two edges. This one is 1, and this one is 1 also. Any ideas on how we should work with this? How to solve this problem? Like a small hint to that, if you will see, if you will look to the queue always has this state. There are vertices with the like at the beginning, the vertices with the distance d, and the vertices with the distance d plus 1, and that's all. You never store in the queue at the same time two vertices with the distance more than 1. So d plus 2 cannot be here.
Should it be using Bfs also, or something else?
Yes, how to change Bfs in such a manner that it will work on this problem.
Well, maybe we could at first add only those edges with distance to them as 0.
Okay, so let's consider the Bfs algorithm, right? You take the vertex u, which lies at the beginning of the queue. What you are doing next? You take u, and then what do you do?
Take all its edges.
What?
Well, loop iterate through all of its
Okay,
edges
good.
and put them to the queue if we didn't visit. Oh well, if we don't know the distance to those.
Yeah, but there can be two choices, right? Either their edge is 0 or their edge is 1.
Here, yes.
Yeah, so it's a little bit more complicated than just add to their end. Like this should be as the hint that it always stores the d first and then d plus 1, the distances. So you took u with distance d. So you iterate over all their edges, and suppose if uv.cost equals to 0, then you know that du, and if du is dw is bigger than du, then you should do something. You set dw to du, and what would you do next? So you know that w has the same distance as u.
Well, do you mean that we...
What should we do with the q? It is not necessarily q in this case. You still want to remain an invariant that these are here and d plus 1s are there. So if you got to the vertex with the same distance,
well, we should need to iterate through all of its edges after that. So maybe we should add it to that structure which stores all the d's.
Yeah, so we just add it to the front. So it will become now not the queue but DAC. There are two options. Either if the distance is 0, then we should put an edge to the left. If the distance is 1, then we should put to the right. And that's it. So kind of in this case you just queue push front w, and then else, I mean, if the uv cost equals to 1, then if dw equals to -1, then we say dw equals to du plus 1 and q push back W. So it's either you put it here, put it here. The only problem, there is some problem, like some not very nice problem in this algorithm, is that each vertex can be twice in this, in the queue. It can be added once as with the distance 1, you put here, and as the distance 0, when you have like the cost 0. So V can be somewhere here and somewhere here. But it's not the problem. It can appear only twice. It cannot appear more than 2 times in this queue, luckily. Because if you add it in the first case only if you improve the distance. Then when you come to this vertex again, you will not change anything because its distance is already calculated and you passed over all their edges.
How will everybody say about the bed?
Okay, so is it here?
Yes.
Yeah, so if I will improve the graph so that the weight can be from 0 to k, it will be a little bit more complicated, of course. Yeah, let me say so. So our structure will be like D, like the vertices on the distance D, and the vertices on the distance D plus 1, and etc. And the vertices on the distance D plus k. And then you kind of store these queues together. Then you take a vertex from D. You iterate over the neighbors and you put the vertex in the, like their neighbor in the corresponding queue with the right distance to them. And by that, in the time kn plus m, we can complete the algorithm because why kn is that because one vertex can appear in all these sets but only once at the same time. Because it was like added from, it was updated from another place, so like there is a possibility that V will be everywhere. And then ym, because for each vertex we iterate over its neighbors only once when the first time we take it from the queue. And then when the queue D is empty, we create D, like we go to the D plus 1, and we create a new queue D plus k plus 1. We go there. Okay, so that's how you deal with when their weights are bounded and that are integers. That moves us to the next algorithm. So you are given a graph. And we have the weight of each edge. So like, I don't know, 14, and you want to find, and you know that the weights of each edge, weights of UV, bigger or equal than 0. This will be the important thing for the next algorithm, and I will explain why at some point. And you want to take one vertex V and count the shortest distance to all other nodes. At first we will talk about Bfs algorithm. How it will work? We will kind of finalize their distance for each vertex one by one. So suppose that we finalize, so we have this V and we finalize the distance of all of these vertices, and there is some vertices left. And you store their tentative distance to all these vertices. So kind of, let us store, so we know that these vertices are already the correct minimums. This vertices has the correct values. So kind of this is their tree of the shortest paths from V. Which vertex can we add to this set? We can add the vertex for which the current tentative distance is the minimal one. So what is the tentative distance? Is the distance, so we have D here, the distance to this node here is D, and this is D plus weight xy. So if it's x, it is y, then D plus w xy. And we take for each vertex kind of the minimal tentative distance. The tentative distance is the distance in this set plus one edge. Why we are ready to add this vertex y to the set of their already computed edges? Suppose that y has some other path from V that is smaller, that is suddenly smaller than this D plus W xy. So let's look on the first time when we cross this border, when we cross the border of this known set. We know that this vertex was not the minimum. This one was minimum, the minimal distance from this set. So this one already less than, oh sorry, it is bigger than this distance. And then you add some path which by their statement of the problem is at least 0. Then this path will be larger than this path. So you just get the minimum and you add u there. And you continue. So let's write an algorithm. So we have distance plus infinity, then you say dv equals to 0, then for 1 to n, do like we know each time we add one vertex to the set, so we have n iterations of that. Then we find min v. To find minimum, we go over all the. Oh yeah, and we have an array was, which filled with false. From 1 to n, if min v equals to -1, no, not like that. If we didn't take this vertices yet, so if not was j, and min v equals to -1, or d of min v bigger than d of j, then we say min v equals to j. So this one, it finds their vertex with the shortest tentative distance. So we just iterate over. If we hasn't taken this vertex yet, and if its distance is less than the distance to the current minimum, then we take it as the minimum. Then we say that was mean v equals to true. And then we should update all the tentative distance that are coming through this new vertex. So we go for j equals 1 to n. We say d of by j. No. We just go over all the edges mean v u in there e, and we say d u equals mean du and d mean v plus weight of this edge. So you find the minimum over the tentative distance, and you iterate over all the edges that are outgoing of it to update the tentative distance of other vertices. Kind of relax the tentative distances by adding one vertex and like by coming from the one distance set with one edge. Is it clear?
Mm-hmm.
So what will be the complexity of this algorithm?
Well, actually, the initial thing has two loops, which are by n, so it should be n squared.
Yeah, so this works in n squared plus m. I mean, n squared is bigger than m, so like this really don't care, this m. But suppose that we want to improve, like this kind of works if the graph is dense, so that the number of edges is pretty high and it is almost n squared. But if the number of edges is much less than n squared, then we can improve this algorithm to O of m logarithm n time. Any ideas how to do that? Like what really we're doing here? We take the minimum from the set and we iterate over all the edges. What data structure can support finding the minimum in cluster? Yeah, for example, heap. So instead of going over this one, you just take the heap and you take the minimum out of the heap in logarithmic time. Then you go over all the edges and try to update the distances to other nodes. And these distances will be updated also in logarithmic n time. Then like this will be changed to logarithm n, and this thing will be changed to logarithm n. Then as you can see, this like there will be no loop here, but there is only loop here, so we have for each edge we update the distance only once in logarithmic time. Since we have m edges, the running time will be m logarithm n. Okay. So this is Dijkstra. So we're like running very, very fast to finish this topic. Probably even faster than I thought. So, but what would we do if there can be negative edges? For that, we can come to an interesting algorithm, which is named Floyd Algorithm. And what it will do, it will calculate the dynamic programming, that is, this is the shortest distance to the vertex U with no more than k edges. Path with no more than k edges. So how to recalculate that? So like it will be kind of simple. For k equals for 0 to n, like it is clear that n is at most, because the number of edges in the path is at most n minus 1, to be more precise. In the graph with n vertices, you have only n minus 1. The path from the vertex v always comes less than. Okay, so you go over k, then you go through all the vertices, then you go through all their edges, and then you say dp k plus 1 of u equals mean of dp k plus 1 u and dp k v plus the weight of the vertex edge v. So it's simple dynamic programming algorithm where we kind of add one edge, and we consider then the state less than k plus 1 edges is there k edges plus another edge, possibly. Oh yeah, sorry, I forgot. Here we should say that dp of k plus 1 equals dp of k. Yeah, of course I forget about that. Kind of we initialize each level as the previous level. Because like it is either the distance k plus 1 or the distance could remain the same from the previous time. So that is why at first we copy here, and then if we take one edge more, then it is either what was previous or one more edge we add there. Okay, I think it's pretty clear how to do. If you need how to do this dynamic programming where their path is k edges, which is not less than equal. Like we want to calculate the dynamic programming where we want for each vertex to find the shortest path of exactly k edges.
We shouldn't do this thing.
Yeah, we shouldn't do the copying.
Yes.
Just we throw away and everything will remain the same. Can you tell me the complexity?
It should be v multiplied by e.
Yeah, v multiplied by rate. Because we make n iterations, and in each iterations we iterate over each edge once, so it is v times c or n times n, as you wish. But typically that is not how Ford-Bellman is written. Like the dynamic programming is good. So if less than or equal to k, then dpn will be already fine for us. Oh, okay. No, one more question. How to check that there is a negative cycle?
A negative cycle is with all negative weights?
No, the negative cycle is the cycle which total weight is negative.
Using this dynamic program.
Yeah, you can do some something else also. Why I'm telling this is that because if you have a negative cycle, then all the vertices that are reachable from this negative cycle will have like minus infinite distance, because you can always get here and iterate over this negative cycle and then go to it.
Well, my thoughts are, if in some algorithm we have visited vertices, and from some vertices we see the visited vertices, and it appears that the weight, the distance to that visited vertex is smaller than it was, then we have some cycle, some negative cycle.
Yeah, exactly. So if we iterate once more, if we iterate this cycle once more, the nth time, and if some vertex has different distance, then there is a negative cycle. Why so? Suppose that, like, you know, this is dp of n minus 1, and this is dp of n. If nothing has changed between these two, then the distances are fine, because each next time you will get the same distance array, because you iterated through this one, get the same, and then if you iterate through this one, you will again get the same, and etc. So it never will change. But if we have a negative cycle, then at some moment it should have changed, but not here. So if there is a position where they are not equal, then there is a negative cycle.
Okay, yes, that makes sense.
Yeah. So, but however, it is not exactly how it is usually written. You can see that this algorithm have a little bit of complication, is that it uses n-squared memory. That is probably not nice, and we should do with smaller memory footprint. And it appears that we can throw away this dimension at all. The algorithm will become the following. So change change equals to false, sorry, equals to true, while change equals to false. And then we iterate through all their vertices. We iterate through all the edges. If distance of u bigger than distance of v plus w vu, we say change equals to true, and we say d of u equals d of v plus w vu. So why the changes here? Like kind of we have a lot of iterations of the following form. We iterate over all their edges and tries to update the distance. And then if nothing has changed at all through the whole, we can stop. So this is why we have while change here. Obviously, if there is no negative cycle, then the number of these iterations will be at most n. But if we have negative cycle, it will never stop, because it will be improved each time. I think this is pretty clear that it works, because on their, suppose we are on iteration k, on the k iteration, d will store the shortest distance of at least k. Like it already iterated through 1, 2, 3, 4, 5, and etc. k, and possibly some paths with which are longer than k. For example, in this case, there is an interesting, like Floyd Bellman works very kind of randomly depending on the order. So for example, suppose we have this graph, and if we iterate through the vertices from left to right, we are done in one iteration. Because you will take this vertex, you update this one, then you update this one, then you update this one, and etc. And that's all. On the next step, nothing will change. But if you do this from vice versa, from the right to the left, then there is nothing to be updated here. Oh, we updated this one, so it will be 0, 1 plus infinities. Then again, from right to the left, it will be 0, 2 plus infinities. Then 0, 3 plus infinities, and etc. And it will take linear number of iterations. But no more, because their path is no more than n minus 1. So this is kind of like, we get rid of their second dimension and it becomes faster in some sense. Because previously we worked like layer by layer, and now all our layers are kind of in some mess in between everything. Okay. I think that's it for Floyd Bellman, and then like I will not dig into how to find the negative cycle here. Oh yeah, I forgot one thing. Do you understand how to restore the path? What we should do? If we, in Dijkstra or in Floyd Bellman, we want to restore their best path to the vertex.
should we store something inside the algorithm?
Yeah.
Well, I guess for Dexter, for example, we should store the edit minimum to the well to our
you can see that Dijkstra and Fort Bellman is really dynamic programming algorithms. How do we do that with dynamic programming algorithms?
Well, also, I guess each time we will make an update in the minimum, we should store.
Yeah, exactly. Every time we update the minimum, we store like from the array from that gives you from where were the last jump to that. So, and finally, the last one, the last algorithm that we were going to talk about in this course is Floyd algorithm. So what is the problem now? The problem that we want to compute all pairs distance. So the previous problems were SSP, single source shortest path, which means that there is only one vertex from which we want to calculate. And this one, a PSP, all pairs shortest path. So we want to calculate for each pair of vertices the distance between them. Now I will write the magic algorithm that suddenly works. You can, and we will talk about that. So we have array D, which is equal to the adjacency matrix at the beginning, and then for I for So we have three inner cycles, Kij, and then if Dij is bigger than Dik plus Dkj, then change that value. You possibly want to wonder why K is outside, because if we remember what had in their dynamic algorithms, where we just have for I, for j, and k, like kind of the middle vertex in the beginning were in as an inner step. But however, if you put it here, it will not work. You should have a kind of additional loop that, like with logarithm of n iterations, kind of the distance between I and j, and the number of edges between them is 2 in the power of k. Because each time we kind of double the distance in the number of edges, kind of like this one. This one is less than 2 in the power of L. This one is 2 in the power of L. Then this one is 2 in the power L plus 1. The new one. But why? And your total complexity will be of n cubic logarithm n, which is not very nice. Suddenly, if you put the order of the loops in this manner, this algorithm will work in cubic time. And that's it. This is exactly what. The intuition behind that is a little bit more complicated. It is still dynamic programming, but a little bit different. So at each step, dij is the shortest path between I and j, and all the vertices on the path, with all the vertices less than or equal to k. So you have vertex I, there is some path vertex j, and here each of the middle vertex is less than k. And you can see here, this is exactly what we are doing. We know, like, we want to give from k to k plus 1. Then we want to have the shortest path between I and j with all the vertices less than or equal to k plus 1. Then, let it be less than k. So suppose that k lies somewhere on the path between I and j. Then, it is k, it is j. Then everything here is less than or equal to k, is less than k. All the vertices here are less than k. And all the vertices here are also less than k. Then we just compare if dij bigger than from I to k and from k to j. And if it is smaller, then this is the real distance.
Do you mean less than k in like order way, or what?
No, less than k, I mean that all the vertices on the path between I and k are the vertices with index less than k.
Yeah, yeah.
Or identifier, or what do you want. So we kind of iterate. So on the first step, the only possible paths are either ij or I1j, only these paths. Like after the first step. Like only the path that goes through 1. Then the path that can have 1 or 2, then the path that can have 1, 2, 3, the middle, and so on. Finally, at the end, you will get the shortest path between I and j with all the vertices less than or equal to n, and this means that we have visited all the vertices there. Did you get it or not?
Well, could you repeat the thing about the order? So if you have all the vertices less than k on the left of k and on the right of k.
So we want to so suppose that we know the shortest path between I and j with all the vertices less than k. Suppose we calculated this previously. Now we want from k. Now we want like it to be less than k plus 1, okay? Then we allow our paths from each vertex to another to go through k. To go through vertex k. Then what's happening there? So how the path looks like? It's from I to k and from k to j. But we allow to pass, like instead of k, we allow to pass only through the vertices that are less than k. That is why we can use their pre-calculated dynamic programming that will say from I to K and from K to J.
Okay.
Yeah, so like the algorithm is pretty simple, but it's a little bit complicated to understand what's happening behind this. So for example, how to find, is there a negative cycle in the graph? So we run this algorithm and we want to check whether there is a negative cycle in the graph.
Well, in this setup, I guess we could just look at the DII, for example.
Yeah, exactly. We can look at DII, and if it is negative, then we have a negative cycle. There is a little bit of complication, suppose like how to restore the graph. So there are two ways, but the easiest one is that we just say at the beginning here that from ij equals to I, and then kind of we store the last edge on the path that we will store there. We will store like not the division vertex, not the K that divided the path into two parts, but the last edge on the path. So in this case, from ij equals to from kj, because like the last, so we have this as the path, and the last edge on the path from I to j is the last edge on the path from k to j. Then you store just that, and that's it. To restore the path, you just go from ij, then from ij, and etc. You just restore one path or one edge per step, starting from the end of the path. Okay, that's it. I think like this was the first lecture on the shortest path. On the shortest path, typically taught in 2 different lectures, but we did it. Probably there is some problems in understanding what happened, but I hope it was fine. Okay, thank you very much for coming. Like, I want to remind you that you have to finish your obligatory tasks, and if you will finish everything on them, then you will get your A. If you will not finish, then we will talk on their exam, which is January 17. And that's it. See you, bye.